This is the lecture for Part 1 of Section 3.1, Definition and Examples of Rings. We've seen that the arithmetic on the set Z sub n of the congruence classes modulo n satisfies many of the same properties as the arithmetic on ordinary integers. We want to now abstract the common properties of the arithmetic on these systems to develop a general theory that will apply not only to these two sets, but also to many other sets. This will provide a more efficient means of studying these systems, since results proved in the abstract setting will then apply to all the systems included in the general theory. Also, it is often easier to see why a particular property holds in the abstract setting. We start by requiring only the minimum number of properties for a system to resemble Z or Z sub n. So here's our definition of a ring. A ring is a non-empty set R together with two operations, addition, which is denoted with a plus symbol, and multiplication, which is denoted by a dot, that satisfy the following axioms. So we'll label these R1 through R8. So R1 is closure under addition, which states for all AB in R, A plus B is in R. So the sum of any two elements in the ring R belongs to R. R2 is the associative law of addition. For all ABC in R, A plus the quantity B plus C is equal to the quantity A plus B plus C. R3 is the commutative law of addition. For all AB in R, A plus B is equal to B plus A. R4 is the existence of an additive identity, and this states there exists an element 0 sub R in the ring R such that for all elements A in R, A plus 0 sub R is equal to A. And R5 is existence of additive inverses. For each A in R, there exists an element n in R such that A plus n is equal to 0 sub R, which is the additive identity. R6 is closure under multiplication. For all AB in R, A times B is in R. R7, the associative law of multiplication. For all ABC in R, A times the quantity B times C is equal to the quantity A times B times C. And R8 is the distributive laws, and there's actually two of them. So for all ABC in R, A times the quantity B plus C is equal to A times B plus A times C, and A plus B quantity times C is equal to A times C plus B times C. Now we can require additional properties to obtain special types of rings. A commutative ring is a ring R that satisfies the additional axiom. We'll label it R9, the commutative law of multiplication. For all AB in R, A times B is equal to B times A. So just a ring by itself does not necessarily satisfy the commutative law of multiplication. If we do have this additional property, then we call it a commutative ring. A ring with identity is a ring R that satisfies the additional axiom R10, the existence of a multiplicative identity. So there exists an element 1 sub R in R such that for all elements A in R, A times 1 sub R is equal to A, and 1 sub R times A is equal to A. Next, I want to talk a little bit about procedures for verifying the ring axioms. So the ring axioms are rewritten in symbolic form below, and then following each symbolic form is the procedure to be followed when verifying the axiom. So R1 is closure under addition, and we need to show for all AB in R, A plus B is in R. So to prove this axiom, we would suppose A and B are arbitrary elements of R. We then need to show their sum, A plus B, is also contained in R. And this requires showing that the sum A plus B has the form required for elements of R. And that's going to depend upon the specific set that we're looking at. R2 is the associative law of addition, and we need to prove for all ABC in R, quantity A plus B plus C is equal to A plus the quantity B plus C. So to prove this, we start by supposing A, B, and C are arbitrary elements of R. We then need to prove the equality. And to prove an equality like this, we can start with one side and show that it equals the other side, or we can show that both sides equal the same quantity. R3 is the commutative law of addition, and we need to prove for all AB in R, A plus B is equal to B plus A. And for the proof of this, we suppose A and B are arbitrary elements of R. We then need to prove the equality A plus B is B plus A. And the procedure for this axiom will be similar to that for R2. We start with one side of the equality and show it equals the other side, or we show that both sides equal the same quantity. R4 is the existence of an additive identity, and we need to show there exists a 0 sub r in R such that for all a in R, a plus 0 sub r is equal to a. And to prove this, first note that this is an existential statement, so we need to first find an element which we believe is an additive identity, and then verify that it satisfies the required conditions. So if we set this up using this two-column approach, we need to first find a 0 sub r, and then we need to verify that 0 sub r satisfies. The two conditions are the domain, 0 sub r must belong to the set R, and the propositional function, it must satisfy for all a in R, a plus 0 sub r is equal to a. Now, to find 0 sub r, we usually start with the equation a plus 0 sub r equal a in the propositional function, and then solve it for 0 sub r. And then once we've found 0 sub r, we need to show that it satisfies the two conditions. For R5, the existence of additive inverses, we need to show for all a in R, there exists an n in R such that a plus n is equal to 0 sub r. And to prove this, first note that this starts with the universal quantifier, so we're going to suppose a is an arbitrary element of R to start with. We then need to show there exists an n in R such that a plus n is equal to 0 sub r. So this is now an existential statement, so we need to first find an element which we believe is an additive inverse, and then verify that it satisfies the required conditions. And so again, setting this up with this two-column approach, we need to find an n, then we need to verify that n satisfies the domain, n must belong to the set R, and the propositional function, it must satisfy a plus n equals 0 sub r. And to find n, we usually start with the equation a plus n equals 0 sub r in the propositional function and solve for n. And then once we've found n, we show that the element satisfies our two conditions. Next, we have R6, closure under multiplication. We need to show for all a b in R, a times b is in R. And we suppose a and b are arbitrary elements of R. We then need to show their product, a times b, is also contained in R. And as with axiom R1, this requires showing that the product a times b has the form required for elements of R. Now the procedure for proving R7 and R8 will be similar to that used for R2 and R3. So R7 is the associative law of multiplication. We need to show for all a, b, c in R, quantity a times b times c is equal to a times the quantity b times c, and our two distributive laws in R8. So we need to show for all a, b, c in R, each of these two equalities holds. Now note the difference in structure between axioms R4 and R5. In R4, the existence of an additive identity, the existential quantifier comes before the universal quantifier. This means we have to find one element 0 sub r such that for all a in R, a plus 0 sub r is equal to a. We then suppose a is an arbitrary element of R and verify the equality a plus 0 sub r is equal to a. In R5, the existence of additive inverses, the universal quantifier comes before the existential quantifier. This means we need to start with an arbitrary element a in R and then find an additive inverse element n for such an a. For each element a in R, we'll have a different additive inverse element. Next, we want to look at some examples of rings. Well, the set of integers z with the standard addition and multiplication is a commutative ring with identity. We modeled our definition of a ring after the integers, and so this is not surprising. And this follows from our assumptions about the properties of the integers. So we assume the axioms of a ring hold for the integers. For another example, the set z sub n of congruence classes modulo n with the addition circle plus and multiplication circle dot is a commutative ring with identity, and this follows from theorem 2.7 in section 2.2, where we verified the axioms of a ring. For another example, let's let R be the set containing 0. So this is the set consisting of the single element, the integer 0, with the usual integer addition and multiplication. Then R is a commutative ring with identity. Okay, so you can sit down and verify each of the axioms, and the ring has additive identity 0 sub r will be just 0, and multiplicative identity 1 sub r is also 0. So the set contains only a single element, so both of these equal to 0. And as I said, you can sit down and verify each of the axioms hold. For instance, for closure, we have to show that the sum of any two elements in R belongs to R. Well, there's only one element in R, 0. And when you add 0 to itself, you get 0. So that belongs to R, and so on. So for instance, to prove R10, the existence of the multiplicative identity, we need to show there exists an element 1 sub r in R such that for all a in R, a times 1 sub r is equal to a, and 1 sub r times a is equal to a. Since 0 is the only element in R, and 0 times 0 is equal to 0, then R10 holds with 1 sub r equals 0. Okay, needless to say, this is not a particularly interesting ring, and this is included here only as an example to be excluded from some definitions later. Okay, so this will come up a little bit later. For another example, a little different than what we've encountered so far, let's let M sub 2 of R be the set of all 2 by 2 matrices with real entries. So M sub 2 sub R is a set of 2 by 2 matrices A, B, C, D, such that the entries in the matrix A, B, C, D are real numbers. So the subscript 2 refers to the size of the matrix, and the R tells us where the entries are coming from. And we have operations defined as follows. For each A and B matrices, for addition, A plus B is obtained by adding the entries component-wise or entry-wise. And multiplication, A times B, is the usual matrix multiplication as shown. And we want to show that M sub 2 of R is a non-commutative ring. So to show that M sub 2 of R is a ring, we need to verify the 8 ring axioms. And here we'll verify just a few of the axioms to illustrate the procedures. It's obviously a very long and tedious procedure to verify that a set is a ring, okay, since you have 8 axioms altogether. So we'll just do a few of these. So first we have closure under addition, and we need to show for all AB in M sub 2 of R, A plus B is in M sub 2 of R. So to prove this, we suppose that A equal ABCD and B equal EFGH are arbitrary elements of M sub 2 of R. And we need to show that A plus B is in M sub 2 of R. Well, from the definition of the matrix addition, A plus B is going to be the matrix with entries A plus E, B plus F, C plus G, and D plus H. And now since A, B, C, D, E, F, G, and H are all real numbers, then the sums A plus E, B plus F, C plus G, and D plus H are also real numbers. It then follows that A plus B has the form of a 2 by 2 matrix with real entries, and so A plus B belongs to M sub 2 of R as required, and therefore R1 holds. For R2, the associative law of addition, we need to show for all matrices A, B, C in M sub 2 of R, the quantity A plus B plus C is equal to A plus the quantity B plus C. So we'll suppose that A equal ABCD, B equal EFGH, and C equal IJKL are arbitrary elements of M sub 2 of R, and we need to show the quantity A plus B plus C is equal to A plus the quantity B plus C. So we'll look at the left side, and this is the matrix, the quantity A plus B plus C. And so we're going to add A and B first, and we'll obtain the matrix A plus E, B plus F, C plus G, D plus H. And then we need to add the matrix C to that. And so we're going to have the matrix shown. So the entries are the quantity A plus E plus I, the quantity B plus F plus J, the quantity C plus G plus K, and the quantity D plus H plus L. The right side is A plus the quantity B plus C, and this is the sum shown. And so we add the matrices B and C together first, and so we obtain the matrix A plus their sum. The sum of B plus C is the matrix with entries E plus I, F plus J, G plus K, and H plus L. And then we add these two matrices together, and we're going to obtain the matrix shown with entries A plus the quantity E plus I, B plus the quantity F plus J, C plus the quantity G plus K, and D plus the quantity H plus L. Now, since real number addition is associative, then the entries in the matrices on the left and the right are equal. So the top left entry on the left side is the quantity A plus E plus I, and that's equal to the top left entry on the right side, which is A plus the quantity E plus I. So our two matrices are equal, and therefore R2 holds. Now the proof of R3 will be similar to that for R2, and will follow from the fact that real number addition is commutative. So next we'll look at R4, the existence of an additive identity. So we need to show that there exists a matrix, and we'll call it Z here, in M sub 2 of R, such that for all A in M sub 2 of R, A plus Z is equal to A. So in the definition of a ring, the additive identity is denoted by 0 sub R, and that's doesn't really fit for the set that we're dealing with here. So we'll use the letter Z to denote the additive identity. So we need to show there exists an element Z in M sub 2 of R, for which for all A in M sub 2 of R, A plus Z is equal to A. And so we need to first find a matrix Z and then verify that it belongs to our domain M sub 2 of R and satisfies the propositional function. Okay, so our first step is to find Z, and for this one, well, we all know what the additive identity is going to be, so we'll just choose it. Okay, so we don't really have to do any work to find the additive identity. In some examples or problems we may have to, and we'll see some examples of that later. But for this particular example, we'll just go ahead and choose Z. So Z is the 0 matrix with all entries 0. And then we have to verify that Z satisfies our domain and our propositional function. So starting with our domain, we can say that since 0 is a real number, then Z has the form of elements in M sub 2 of R. Namely, it's a 2 by 2 matrix with real entries. So Z belongs to M sub 2 of R. Next, we need to verify the propositional function. For all A in M sub 2 of R, A plus Z is equal to A. So to prove this, we'll suppose that A equal ABCD in M sub 2 of R is an arbitrary matrix. Then A plus Z will be our matrix A, ABCD, plus Z is our 0 matrix, 0, 0, 0, 0. And this is going to be A plus 0, B plus 0, C plus 0, D plus 0, which is just A, B, C, D, which is equal to A. And so the propositional function holds, and this proves the existential statement, and so therefore R4 holds. Next, for R5, this is existence of additive inverses. We need to show for all A in M sub 2 of R, there exists an N. We'll use a capital letter N in M sub 2 of R such that A plus N is equal to Z. So let's suppose that A equal ABCD is an arbitrary element of M sub 2 of R. We need to show there exists an N in M sub 2 of R such that A plus N is equal to Z. So we need to find an N and then verify that it belongs to M sub 2 of R and satisfies the propositional function. So we first find an N, and again, we're familiar with matrix addition, and so we don't really have to do any work to find our N. We can just go ahead and write it down. So we're going to choose N to be the matrix minus A, minus B, minus C, minus D. And then we need to verify that N satisfies our two conditions. So first the domain. And we can say here that since A, B, C, D are real numbers, then minus A, minus B, minus C, minus D are also real numbers. So then N has the form of elements in M sub 2 of R, namely it's a 2 by 2 matrix with real entries, so N is in M sub 2 of R. For the propositional function, we need to verify that A plus N is equal to Z, our additive identity. So A plus N is the matrix A, B, C, D, plus the matrix minus A, minus B, minus C, minus D. And when we add these, we're going to get A plus minus A, B plus minus B, C plus minus C, and D plus minus D, which is the 0 matrix, 0, 0, 0, 0, which is our additive identity Z. So the propositional function holds. And so this proves the existential statement, and so therefore R5 holds. Now, after verifying all 8 axioms, we can then conclude that M sub 2 of R is a ring. So now finally, to show that M sub 2 of R is non-commutative, we need to show that it does not satisfy R9, the commutative law of addition, multiplication. For all AB and M sub 2 of R, AB is equal to BA. And to show this, we just need to find a counterexample. So for instance, we're going to let A be the matrix 1, 2, 0, 0, and B be the matrix 1, 0, 1, 0. These are chosen pretty much at random. Then A times B is the product 1, 2, 0, 0 times 1, 0, 1, 0. And this works out to be the matrix 3, 0, 0, 0. BA is the product 1, 0, 1, 0, 1, 2, 0, 0. And this works out to be the matrix 1, 2, 1, 2. So therefore, A times B is not equal to B times A, which shows that M sub 2 of R does not satisfy R9 and hence is not commutative.